Let's look at learning objectives B and D. We're going to determine if a graph is considered growth or decay, and then define the exponential model's rate and factor. Now, what you want to recall back from Algebra 2 is that an exponential model is so because of the format. This format is in function notation, but if I put it just with y equals, you should be used to seeing something that says y equals a times b to the x power, where b is considered the growth or decay factor, and a is the starting amount, and then y is going to be our ending amount. So if you look at the 6 graphs at the right here, I actually have the equations for each of them assigned. So if we look at letter A, the graph is here, and we can tell by the picture, you just read it left to right like you would a book. If you read it left to right, you're going to see this one growing, so graph A is considered a growth function. You can actually see it in the equation. If you look at the equation, if you look at the growth or decay factor, which is raised to the x power, it's a 2. So that is greater than 1, therefore it's considered growth. If you look at the equation for graph B, you're going to actually look at the factor right away. This factor is less than 1, therefore we can tell it's decay. And if you look at it this way, you're going to actually see it shrink from left to right, so B is a decay function. And if we continue doing that, be careful when you look at equation C, it only has 3 to the x power. We're not seeing the A and the B both. The A is actually there, it's just 1. If you look at the graph, you're going to see it grow, so C is also going to be a growth function. If you look at D, the factor is 0.5, which means it will be decay because it's less than 1, and you see it shrink. If we look at E, we're going to see that the growth factor here is a 3, greater than 1, and you actually see it rise. Now this last one's a little bit trickier. If you look at the formula, the base number, or the B here, is actually less than 1, so it's decay. But if you look at the graph, it actually looks like it's growing. So you have to be careful on this one. This one does end up becoming a growth function, though, because we're starting with a negative amount. If we take a negative amount and you cut it in half, you're going to get less of that negative amount, which is a bigger number. But again, look at the graph, and if you look at it and you see it move left to right and grow, it's a growth function. So in this case, it is important at times to actually look at the physical graph also. So let's continue looking at this function notation. Again, it was y equals a b to the x power. We know again that this is an exponential function because the x variable is the exponent. That's what makes it exponential. Let's formally define what we talked about before on the previous slide. We said if this base number here that is raised to the exponent, if it's greater than 1, and if a is greater than 0, it's going to be growth. An exponential, be careful for decay if we said it's less than 1, but it does have to be greater than 0. So this base number is between 0 and 1, and in this case, again, if a is greater than 0, it will be decay. Now, there's actually a more detailed format for the formula of y equals ab to the x. It's this one right down here. And I'm just going to use it again. I'm going to rewrite it as a y, so we see it like this. So let's do y equals p to the 1, and I'm going to do plus or minus r to the t. So let's adjust that. We're going to have to decide if it's plus or minus. The thing about this formula that's nice, this p-value right here is really the same as the a, or the initial starting amount. So I'm going to put the starting amount right here. So that didn't change at all. Notice this, where b is, how it's raised to the exponent, this whole value is raised to the exponent. We're just calling it t this time. So 1 plus or minus r is actually our factor. So this is the same as the b. Okay. Now, the nice thing about having the details of the factor is we can actually look at the rate inside of it. So when you see that, this r value is called the growth or the decay rate. Now, in the first format we looked at, we don't see the rate. It's going to be embedded inside of there. In this format, it's actually broken down. It's whatever number was added or subtracted from 1. And then the last thing is t is just our time. And it's either going to be time in days or hours, or however the problem defines it. So let's actually look at the exponential functions given the more condensed format, but also when we do, we want to be able to read from it this a little more detailed format, so I'm going to jot that down. Because you're going to be asked what is the factor and what is the rate. So for this first equation, if a is 4 and b is a 0.6, I'm going to write the equation. It's going to look like this. And we'll do to the x power, or we could do t. Now the factor on this is right here. And this is a decay factor. And the decay factor on this is going to be 0.6. Now what was the rate? The only way to get the rate is to take the factor, which we had was 0.6, and set it equal to either 1 plus r or minus r. Well, this is decay, so it's 1 minus r. Well, what was r? If you solve this algebraically, what you'll end up getting is you're going to take 1 minus 0.6, so what we get from this is that the rate had to be 0.40, which is the same as saying 40%. So this had a decay rate of 40%. Okay, let's look at this next one. If a is 1/2, so I'm going to write that, and b here is 1.3, and we'll use to the x power. Again, I can look at the factor, and I see that it is growth, so it's a growth factor. The factor here is going to be 1.3. Well, the question is going to be, what was the rate of growth? Again, the rate is going to be embedded inside this factor. How did they get it? It was 1.3 as the factor. So what they did is they took 1 plus r. Well, to solve this, subtract 1 from both sides. The rate on this problem is 0.3, or a 30% growth rate for this example. Let's look at this last one here. They want the initial starting amount at 400. The b, or the factor, is 2.5, and we'll just use to the x power. Now, is this growth or decay? Clearly we can tell with this it is going to be growth. So this is going to have a growth factor of 2.5. Now, knowing that, what is its rate? Well, the rate, again, the factor was created from it, so they took 1 plus a certain rate. Well, to solve this, subtract 1. R was 1.5. Now be careful, this is a decimal, so to convert it to a percent, you move the decimal place to the right too. This was a 150% growth rate.